this video, we'll discuss examples of proof by contraposition. In a proof by contraposition, we want to show that an implication P implies Q is true. P is the premise, Q is the conclusion. The contrapositive of the implication, which is logically equivalent to it, is not Q implies not P. In other words, the negation of the conclusion implies the negation of the premise. In a proof by contraposition, for the implication P implies Q, we assume the negation of the conclusion, that is not Q, and then we use logic and the rules of inference to show the negation of the premise, that is not P. Another way to think of this is that we state the contrapositive and we prove it directly. And this works because the implication is logically equivalent to the contrapositive. And you can convince yourself of that again by looking at the trig tables for both. So first, for this exercise, we're going to state the contrapositive. So our exercise is the same as last time. It's let n be an integer. If n squared is odd, then n is odd. We're going to do a proof by contraposition, and first we'll state the contrapositive, and we will go about essentially proving it directly. So once again, this is n squared is odd as P, n is odd as Q. The contrapositive is not Q, implies not P. And so first we'll state the contrapositive, so we negate the conclusion. If n is even, then we negate the premise, n squared is even. So now we can begin the proof, and we start the proof with the negation of the conclusion. Basically, we assume that n is even. Okay, assume n is even. That's the negation of the conclusion. That means there exists another integer k such that n is equal to 2 times k. Let's consider n squared. Using substitution, we can square 2k. When we do this, we get 4k squared. We can factor out a 2, and we will get 2 times 2k squared. Since the integers are closed, under multiplication, we know that 2k squared is an integer. And since we have expressed n squared in terms of 2 times another integer, n squared is even. And when we've done that, we have begun at the negation of the conclusion, that's not Q, and we have shown the negation of the premise, that is not P. So we have completed the proof by contraposition. Let's try another example. So assume that y is not equal to 0. So we're going to make sure that y is not equal to 0, and if x divided by y is irrational, then either x is irrational or y is irrational. So our P is going to be that x divided by y is irrational, and our Q is going to be that either x is irrational or y is irrational. So the first thing that we want to do is we want to remind ourselves that we want to take the contrapositive. So that's going to be not Q implies not P. In this example, our conclusion is x is irrational or y is irrational. When we negate that, we have to apply De Morgan's rule, and we will get that if x is rational and y is rational, then their ratio x divided by y is rational. Now that we stated the contrapositive, we can prove it directly. And to do so, we start off with assuming not Q. So just again, this is P implies Q. And we are going to assume not Q. And what this means is assume X is rational and Y is rational. Well, since they're both rational, we know that there exist integers P1, P2, Q1, Q2, such that Q1 is not equal to 0, Q2 is not equal to 0, and P2 is not equal to 0, such that X is equal to P1 divided by Q1, and Y is equal to P2 divided by Q2. Just as an observation, Q1 and Q2 are both not equal to 0 by the definition of a rational number, but we can also assume that P2 is not equal to 0 because Y is not equal to 0. Okay, so now we want to consider the ratio. Let's consider X divided by Y. So when we do the substitution, we are going to get P1 times Q2 and P2 times Q1. Since the integers are closed under multiplication, we know that P1 times Q2 is an integer and P2 times Q1 is an integer. And we also know, since P2 and Q1 are not equal to 0, that their product is not equal to 0. So since we've expressed X divided by Y as the ratio of two integers such that the denominator is non-zero, we know that X divided by Y is rational. And what we have just done is we have shown that the negation of the conclusion leads to the negation of the premise, not P.